right, good afternoon. So if you have your metric sheet, you might want to get that out. Guys, we gauge based on how you're understanding things based on traffic in the SRC usually and how many questions we're having to help and answer with. And definitely we got a huge spike the last 2 days. So I want to just kind of clarify and make sure that we are on the same page with this moving forward. Then we're going to talk about the note sheet that I gave you today. We're not going to make it all the way through, but it'll be pretty close. This will be the last time we're doing anything associated with math, at least new math, for quite some time in chemistry. So some of you that might be a great thing, some of you that might not be, but it's just a fact. We're going to be doing some other things for a little while, but it all applies and it is used. Okay? So, if you handed this in, you're not behind. This is not on your assignment sheet. If we're finishing up conversations, let's get that done so we're ready to go. We have a lot to get through, and I don't want to feel like it's rushed. Ultimately, you need to know a few very important prefixes. What we went through on Monday is really important that you understand that there's base units that you're measuring, like seconds and liters and watts, but the converting part was the part that was giving people a huge challenge. So again, just at least observe it. Hopefully a lot of you have this down somehow in your notes already, but I'm even going to simplify it more. If I make 9 lines to the left, 1, 2, and 12 on the right, and then I number every 3, which would be every 1,000. I'm going to do 2 problems just to reiterate this one more time so we're all kind of on the same page. There are certain prefixes that are vital to us. And all of them that you learned are really important and utilized in different ways in science. What's a billion? They have 9 zeros. So that's 10 to the 9th. You all want more of this on your phones.
Gigabytes.
Yeah. And byte is the measurement, but you're right. Giga. Right? You want as many gigabytes as you can. My phone does not have enough. Every time I take a photo, it says you've run out of space, and then I got to delete like 6. It doesn't make sense. I got to delete 6 more, and then I take 2 more, and then I run out of space again. I'm very confused. What's a million? So like, you might get confused and think it's a million. Like in lottery, they call it the megabucks sometimes. It's usually you're talking about millions. We all need to know 10 to the 3rd. It means 1,000. It's kilo. You got to know kilos, 1,000. All right, then we get to some other ones. Like 1,000th is milli. This is micro, nano, and pico. And then we're going to throw in a couple little ones right here. But notice, besides the D and the C, it's every 3. So it's every 1,000. So let me just show you D and E on the back. And if you finish this all, this is awesome. If not, and you're struggling a little bit, I get it. Some of us, we're just having some problems with that T-chart approach potentially. But I need you to understand it is really important. Potentially in converting certain units as you continue on in math or science. But check this out. 4510, what does this stand for? NS? Nanoseconds. Prefix unit. Check it out. It still says an S, right? Some people have been really confused. Where's the S? It's not on there. That's the measurement. It's nanosecond and millisecond. So I'm going from nano to milli. Which direction do I have to go? That way. To the left. How many times? You can either count it or you just look at the math, the numbers. I have -9, -3, that's 6. So I just take this and I go 1, 2, 3, 4, and then 2 more, 5, 6, those become zeros. So my answer is simply 0.00451, and you could put a 0 if you like. Although technically it's not significant, so I probably shouldn't have done it. The second one, what does big M and W mean? Megawatt. And then the second one must mean milliwatt. So, what am I doing? I am going from mega to milli. So I'm moving it to the right, and I'm moving it 6 here, right? And then another 3. So I'm moving it 9 times. So if I just grab this, I'm going to do it in big chunks. 3, 6, 9. And there I go. It's 90.2. So if that works, great. If you're like, no, I really like the math and the organization of it, great. But what you're going to need to understand is at least this level of chemistry, and what we're going to be covering is that we just need to convert some very specific things, and you should be able to maneuver through that at a decent rate when we start showing you the specific ones you need. Okay? So that's where I'm heading right now. I'm going to go to the worksheet. One question has been brought up. I don't know how to do letter G's on the back. If you don't, that's okay. You can cross those two off. If you've done them, fantastic. It only makes you stronger. Okay? So here we go. Please have the sheet ready. Be involved with me, please. We're going to change pace a couple times. This is much more physics than chemistry. So what I'm teaching you today is what's needed for the chemistry part. So I'm not going full out. If I did 100%, if you took 100% of the material, I'm giving you like, for a high school level, let's say 30%. I don't know where I'm actually cutting that out. But we're giving you the base, the basics for what is needed at a chemistry approach today, okay? So electromagnetic spectrum, it's a fancy way of basically saying a range of different radiation or types of energy. What I'd like you to do before I start asking for some help is please underline what the scale is all based off of. It's based off of wavelengths in meters. Please underline that or highlight it or whatever you like to do. I love the people that bring out highlighters. I think that's cool. You don't have to. So there's a bunch of different energies, okay? I need your help. Any type of radiation, wave, ray, energy that you've ever heard of in a movie, in your normal life, and I will put them on here if they actually fall in here. But there's a lot of things that you could have run into. Again, radiation, a ray, a wave, any kind of energy you might have heard of. Microwave, why not? It goes right here. I can't fit it. I'm sure you can. So it goes in that one. Underneath it, in parentheses, write radar. It's actually what radar is. Please don't find a military base and be like, I'm taking a frozen burrito out there and I'm going to hold it above my head and see what happens. There's radar everywhere all the time. It's like you have to get closer. But that is a microwave, definitely. What do you got? Radio waves. We're going to do two of those right away. TV/radio. That's just that whole area on the right side. So all of that. Good. There's a lot of them more. There's still more out there. Gamma. Gamma. You hear that a lot of times in movies or maybe some sort of a test. Gamma. My dad was a dentist for a long time, or a doctor might use this a lot. X-rays. Yeah, definitely X-rays. All right, there's 3 left, even if it doesn't look like it. Anybody else? Yeah?
Light.
Good. No one said that today yet. We're going to write visible. Down here. Very good. Gold star. No one's come up with actual light yet. There's 2 other ones. One of them where maybe you shouldn't, you aren't, but you should be worried about it. If you get too much exposure to this, it might age you eventually or cause bad things to happen with your cells.
Radiation.
That can't. Well, yeah, these are all radiations. It's UV, ultraviolet. And then I always think this is cool. In a military movie, they pull these out a lot. Really sweet-looking goggles, and they can see like heat signatures of people. You know, like the dark reds to the yellows and oranges. And you know what they're using on that? It's heat. It's thermal. Yeah. It's a more technical. You've heard of it. It's in remote controls. Maybe you don't know that. Yeah. Infrared. Good. Awesome. So those are our types of waves. Now, oh shoot, I brought this down here. On the bottom, we'll talk about this more and more, but this shouldn't be a huge leap already. Just looking at the arrow where it says low energy, high energy, it shouldn't be a huge leap for you to go, oh, okay, so X-rays and gamma rays have the highest energy and radio have the lowest. When I get an X-ray, they have to put a big lead apron over my body and everybody runs out of the building, like out of the room, right? It's not like someone puts on the radio, you're like, no! My sister's pregnant, she's in the front seat, don't, it'll hurt the baby. Like no one's worried about the radio station. It's low energy. X-rays, gamma rays, those are really high energies. But we do have, this is what's crazy, this whole spectrum, the only thing we can see with our rods and cones and how we're built is just this little sliver. This is all we can see. And other animals can see other things. Butterflies. they through mating, they see extra patterns on the back of their wings. Like what we see are really sweet looking patterns. They see even more that come up through being able to utilize ultraviolet radiation, for example. So on the bottom of here, we have two range of colors going from purple, which we call violet, to red. Gentlemen, I know the Mountain Dew is great in a large group, which shouldn't be in here in the first place, but let's not also have side conversations. On the bottom, we have 4 times 10 to the negative 7th. Colors aren't said that way. So negative 7, if I move the decimal 2 times over, I'm at negative 9. What's that prefix? 10 to the negative 9th. We just did them. Negative 9.
Pico.
It's tiny. And it's not pico, it's close.
The one that's
Nano. Write this on the side. I'm even going to do the color. We will write that. Violet will be 400 nanometers. You're going to see that quite a bit. If I go 7 times 10 to the negative 7th, I can move the decimal 2 times. That's 700 nanometers. So, I don't know you know this. I learned this in first grade. There was a guy who invented the rainbow. Not discovered, invented it. He lives in Portland with his wife and his kids. What's his name? Roy G. Biv. Famous, cool guy. Roy G. Biv. Roy G. Biv. Problem is, you've been lied to your whole lives. And I just found out not too long ago. I was pretty upset. It's not Roy G. Biv. It's Vib G. Yor. I know. I'm sorry. Let it soak in. Process. You gotta let that happen because that's hard to know that an American hero actually has not been named the right name this whole time. Vib G. Yor. Why I bring that up is that you need to understand the range of colors in this direction, because when you have this, we're talking about energy. The violet's the highest energy, the red's the lowest energy. The 2 things that students mix up the most are ultraviolet, infrared. Check it out. After I'm at violet, I go past violet, I'm ultraviolet. I go past the red, I become infrared. So the reds and the violets, those are the next stages right off of those actual corresponding colors. So man, I wish there was a song that would help me remember the electromagnetic spectrum. I wish. It's not this song.
Yeah, I can't see it.
The electromagnetic spectrum is just a name for the range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared radiation, visible ultraviolet X-rays, gamma rays. From the TV station to your living room, that is the work of radio waves. Heating food in just seconds, microwaves do that. Heat treatment for illness, take pictures in the dark. They are even in your remote control. Infrared radiation, the electromagnetic spectrum is just a name of a range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared radiation, visible ultraviolet X-rays, gamma rays. Red, orange, yellow, green, blue, indigo, violet. That is the only part of the spectrum that can be seen by us. The suntan on your skin kill bacteria and viruses. Used to detect forgery. That is ultraviolet. The electromagnetic spectrum is just a name.
This will be in your head, even if you don't want it to be.
Radiation, let me tell you what they are. Radio waves, microwaves, infrared radiation, X-rays, gamma rays.
This is my favorite picture of the whole thing, right here.
The work of X-rays kill cancer cells and sterilize dangerous gamma rays do that. Now we have completed the electromagnetic spectrum.
And this is hilarious what he says here.
If you still do not understand, then play the song again. The electromagnetic spectrum is just a name of a range of radiation. Let me tell you what they are. Radio waves, microwaves, infrared radiation, ultraviolet X-rays, gamma rays.
Pull away the cymbal, dramatic.
Radio waves,
Oh gosh, feel that? Man.
infrared radiation, ultraviolet X-rays, gamma rays.
Yay. No one. All right, so on your sheets, I know you can see waves are in the upper right. Don't get confused that mine are in the left. I'm doing it under that title, okay? So we need to talk. You all have some experience with waves somehow, some way. In an ocean, in a lake, at Wisconsin Dells, the big wave pools. So let's talk about that. Put a little dotted line underneath it. It's not my first time. I've done that. So there are some parts to this you need to know. Yes. I'm doing it under a title that you have on your sheet.
I couldn't find it.
Oh, in the upper right. It's in the upper right. We're doing it in the upper right. See the wave title? The wave title? I just literally said that before I started. Yes, you draw it. The bottom. It's called a trough or a valley. It's a Y. T-R-O-U-G-H, trough. All right, I'm not doing any real justice to this because this isn't physics yet, but there are points of basically absence of energy or wavelengths or all that of the waves, not frequency. But those places, it's really sweet if you do some different activities with it. There's no motion at all. It's void of activity. Those are called nodes. If you're a Pitch Perfect fan, I have nodes. Well, then you don't know. From crest to crest, that's called a wavelength. Wavelength. And I'm going to put a symbol underneath, and I will draw it bigger. It's called lambda. Technically, it looks like this. But if you don't want to draw like that, like I refuse to do curves. I make straight lines. It's an upside down backwards Y. Okay? But that's what it looks like. You don't draw two of these. It's a wavelength. That's what, instead of writing the word wavelength over and over and over again, we make a little lambda. Okay? So put a line just how I have it. It's an upside down and backwards.
Yeah, it's upside down backwards.
Right. Well, line. First world problems right here. Finally, how the height of your crest or the depth of your trough, we call that the amplitude. That's like your volume. The higher it is, the louder it'll be in a way. Okay? So that's some anatomy of a wave. We're going to then slide down right below it. There's some waves that are already there. If you already drew on them, I'm sorry. But if this happened in 1 second, we're not going to write a lot on here. But I just want you to see the difference. And this stuff is going to be things that you, as we work on it, hopefully it'll just kind of make some sense. This is a wavelength, or this one, you can pick any one of them, doesn't matter, is a wavelength, right? Like it's smaller on the bottom, right? It's a lot smaller. And we're going to classify and talk about these in a minute, but this is a much bigger wavelength than this one. I'm putting that on the side. Like just arrow up, meaning I got a bigger one, arrow down, I have a smaller one. If I had a dock and these waves were coming in though, which one would crash into my dock much more often? The bottom one, right? So the first one's coming in, right? In 1 second, let's say, I know that was more than a second, the second one, it's happening like that. Okay, it's both happening in 1 second. The difference is, this one's happening much more often. When you do something, hey, I'm on my phone a lot. I'm frequently on my phone. Oh, I infrequently do my homework. Something like that. Maybe it's the other way around. But it's how much you do of something over a certain amount of time. That's called frequency. Your radio station is a frequency. And it interprets the number of waves during a certain amount of time. I'm going to show you the symbol. We'll classify it in a second. It's not a V. That's a V. It's called nu. It's not a big deal, but it's a straight line, and then you curve it. And I know you're like, oh, I'm broken. I cannot do that. We're not going to judge you and take out like, oh, it's not curvy enough. We're not going to care that much. But this is a lot less frequent than that. So if you have a large wavelength, you have a small frequency. If you have a small wavelength, you're going to have a high frequency because you can have more of them because they're smaller. Okay? So, that all being said, there should be some space under this image on your notes right now. Okay? This image right here. Okay, we are going to put an equation right in the middle. Please draw this and box it. We are going to give you 2 equations today. You will not have to memorize either one. We will be giving you those equations. It's about application, not memorization. But you need to understand what they are. Okay? So, this is the relationship of frequency and wavelength. So let's classify and just make sure you're understanding what the heck you're seeing. As you've noticed, we're not big on vocab words. We try to get you into the action as much as we can, but we'll try to classify some things when we need to. So frequency is hertz, or 1 over seconds, or, bless you, I don't know what to say with a hiccup. Or seconds to the -1. Those are all the same units. You don't put them all. It's one of those. So hertz is the easiest one to write, but it doesn't actually have a measurable unit in it. Seconds is the unit. Why is it 1 over seconds? Because it's something per time. Frequency is how many things you do per time. In this case, it's number of waves per second. So that's why it's 1 over seconds. A wave isn't a unit. A wave is a thing. This is wavelength. We just did that one. And it's a length. So it's in meters. I'm not even going to tell you what it is. The name's in it. It's wavelength. Wavelength is the length of a wave. And it's in meters. So what is this mysterious letter C? The relationship, and again, we could go into so much more. The relationship between your frequency and your wavelength always ends up giving you the speed of that radiation. And what's so cool, or not cool, doesn't matter, is all of these types of radiation all travel exactly at the same speed. They all travel at speed of light. And that is also going to be given to you. .0 times 10 to the 8 meters per second. That is very fast. So, what we're going to do right now is I'm going to show you how we use this equation. For those of you that maybe get a little confused on rearranging equations from time to time, if you'd like to rewrite these equations, we're solving for these two. So if I'm solving for frequency or wavelength, it'd be C over nu, or, oops, Or if I'm solving for frequency, it'd be c over lambda. Notice they're both taking speed of light over the other variable. As long as you can apply this, you're going to be fine. We're going to give you this equation in blue. But this would be how you'd solve either one of them. All right, so let's take a look at some examples. I'd like to talk about radio here. So what is the wavelength of... Thank you. All right, so WIXX has 101.1 megahertz, okay? The mega is what we need to know for our prefix. So mega is times 10 to the 6th. So this number, you're going to have to be able to do this. This is where we are utilizing our metric system. The radio station drove out today. I had 101.1 when I first pulled out, and on the side says MHZ, megahertz, but I can only have it in hertz. So that is a frequency. I want wavelength. So what I'm going to do is use my equation that I'm being given, and all I got to do is plug it in. So I'm going to put the speed of light over my frequency. I'm going to be your calculator today. For some of you who are challenged with this though, or you seem to get the wrong answers, you might want to check it eventually on your calculator. For example, you type 3EE8 divided by 101.1 EE6. And when I say EE, I'm not pushing two buttons. I'm hitting E or EE or EXP or whatever it is. Well, how big is that? I can already see the board, but 1 meter, 2 meters, 3 meters, 1, 2, 3. So I don't know how high it is, but it's about that long. And if I keep going, well, that looks sloppy. But this is the length of one wave. I could also talk about waves. Shoot, I didn't pull this quite up high. On the top of one crest, oh wow, to the top of the other, which apparently it's also higher. You can go from crest to crest or node to node. What's the whole point? I'm trying to get across is that you need one crest, one trough. One crest and one trough is a wave. Once you start a new portion that you've already done, then you're starting a new wave. So that would be the length of a wave coming off of the antenna at WIXX, for example. All right. Well, if you've ever taken a road trip with your parents or you've been listening to the radio and it seems like the FM stations start to disappear when you start getting to Wausau or you get closer to Milwaukee, is because there's a lot of reasons for it, but one is that the waves are short. So this other one, to finish this up, is WHBY. This is an AM station. What is K? We need to know this one. 10 to the third. Again, I'm not asking for every one of these. I'm trying to show you the ones you need. This sheet is going to, at the ending of it, you're going to be like, oh, those are the ones that are really going to be utilized in this chapter at least. So I need wavelength again. So I put speed of light over my new frequency. And I get AM stations don't go bad for hundreds and hundreds of miles. Potentially some AM stations can even make it around the world. One reason, not the only one, but it's because of the length of their waves. They're much longer. They're able to maneuver around and bounce off of things a lot easier because of the length of their waves. So you can see a huge difference. It's 100 times larger than an FM. Quickly, let's look at two other ways we can do this. Again, it's just about practice and having an example, so then when you go through your homework, you'll just be able to say, hey, it's like this one, it's like that one, I understand. Frequency, again, that's a new And then I'm given a wavelength. Here's the last one for prefixes today. Nano. Colors are given in nano. We've already done this once, but I'm going back the other way. I can't use nano. It's always got to be in meters. So this becomes 612 times 10 to the negative ninth. So today, 6, 3, and negative 9. Those are the ones you really need to have down. That's going to be negative 9. And then notice, the n's gone. I take the n out. I put times 10 to the negative ninth in. And away I go. So I rearrange it. This is my rearranged equation. It's the same equation every time. I'm just rearranging it. If you put that in your calculator and hit enter, it would magically become 6.12 times 10 to the negative 7th. Just understand that we just didn't want to worry about the decimal. So you just leave it as is. And if you do that right, this number will not mean anything to you. But this is the answer. Now, you get the answer, you're like, I can't remember the unit. The units hurts. But if you look, meters would cancel, and all that's left is 1 over second. So if you forgot, there's no reason that you can't remember, or not remember, but look at the units canceling. You'll start to notice every color has a frequency in the 14s. Most energies are in negative 19 and 19 to 21. Not negative. So we have one more. This is, to me, my favorite one, and the one that will, if you can get this, you're going to do great. And it's not that difficult. Please underline type of wave. Last one on this part, and then we just have one more little thing to do, and then I'll talk about our really fun lab and our world holiday on Monday that we need to celebrate. If you go above, what am I asking for type of wave? If you look back on the top of your sheet, what are all those based off of? I made you underline it. It's the first thing we did today. It's based on wavelength. Half of you, when you get to the test, you will not know how to do this because you won't recognize that when we say type of wave, it'll be based on wavelength. We'll give you the electromagnetic spectrum, maybe not completely filled out. There might be some missing things, but you should be able to figure out what those are. You'll get some practice with it. But you got to realize that's a wave. So, oh yeah, shoot. So I'm going to solve for that. So again, I'm repeating this, but I'm going to show you why I'm doing this problem. And it's really not that much work. It's more about what I'm about to show you here that you can apply it. So that is not answering the question. Can you answer the question based on that information? I'll even give you a hint. That's what you want to worry about. The times 10 negative fifth. If you go above, where does that fall into your electromagnetic spectrum? Infrared. Very good. You're like, wait, what? This is 10 to the negative fourth right here. This is 10 to the negative 7th. That's a huge range, so it falls somewhere in here. So that falls in infrared. If it was 10 to the negative second, or sorry, negative third, let's say, it would be probably microwave. We make sure it's in the middle somewhere on a range. Like it won't be like right on the boundary. All right. So that concludes that part. We have one more little thing. We're not going to do this whole back. We're only going to do half of it. We're going to run out of time. All right, so a guy named Max Planck came up with this idea. You don't see a Ferrari going down the road going like this, really, and you're like, wow, that thing is really awesome. Like, you'd be like, what is wrong with that car? I know you don't have to say it. People have been telling me my whole life I'm very athletic and I walk very fluidly, but I don't walk around like this and, you know, doing robots and all that other stuff. I messed that up. But you're not jerking through your remote as you're walking along and you're like, hey, what's up? You don't have these surges of energy. But the thing is, that's what we are all made up of. We have these surges of energy. And what Max Planck basically talked about, and this is going to help you with our lab on Friday, is objects emit energy in the form of small packets of energy called quanta. One of my favorite shows when I was a kid was called Quantum Leap. It was the #1 show in America for like 3 years, and they jumped into different people's bodies in the past and the future, all this stuff, and he fixed what went wrong, and he made it right. That had nothing to do with this. But he finds out that energy isn't on this smooth plane. It's these packets of energy. And when we relate it to electrons, they jump energy levels when they absorb energy. If I'm going up here right now, some of you, this right here, you're like, that's just too much work. I just can't do that. But if I keep going up, I'm adding more and more energy. And I have a fear of heights, so this is interesting. I'm adding more and more energy to this. And I can prove it because if I fell right now, which unfortunately a few of you are sick enough that you're actually hoping I do, and that's your own issue. Versus if I fell from down here, I'd have a lot less energy just based on my degree of pain probably, right? But I would feel that. So what we're going to start talking about is that if I put my foot in the middle of this rung right here, and I just settle, like, I'm good, this is where I'm going to go, it's not going to whoop, like, it's not going to all of a sudden just go up like, whoa, what's happening? It's going to fall back down because I didn't get enough of that energy to get to that next level. And that all interlinks with what we're going to kind of be looking at. But as I go down then, I kind of come back to a resting state. And what we're going to be focusing on is when electrons jump, they absorb energy, okay? And then so you can, on Friday, we're going to put all these different chemicals that are used in fireworks. Not like, oh, like the ones used in fireworks, like the actual ones used in fireworks. We're going to put them in Bunsen burners, and that energy is going to cause these electrons to jump. And they're going to go up to wherever they go. And when they fall back down, which is in milliseconds, nanoseconds, but to us, we don't know. When they fall back down, it releases the energy that's stored in there. And for all intents and purposes, what you just need to know is a photon comes off, which is basically like a particle of energy that has a certain wavelength that we either see or we don't. So like X-rays, those get shot up really high, and they fall down really far because they have a ton of energy. And those are more dangerous. And all depending on how much energy comes off of it, that's corresponding to this electromagnetic spectrum. So we're going to use an equation that you will be given. Class equation. It's very short. Yes, that's not a V. That's frequency, our good old friend. I'm going to do 1/seconds. The H is given to you. You have two constants. None of them have to be memorized. So why don't you see me like walking through? There we go, I did it right. Why aren't I slowly having these jerky motions? Is because the size of the energy that is emitted, these packets are so tiny that you would never notice it. It looks fluid. But if it's multiplied by a frequency, it's how many times it's released, a way to think of it, at least. And this is the value. Again, I'm not really giving it justice, but what I'm saying. This will be given to you. And it's just a constant. Those two things together, don't be confused by that unit. It's joules times seconds, so if you multiply it by inverse seconds, all you get is joules. Thing is, to me, at least for this chapter, that's the equation. I don't like that equation as much. I want to talk about electromagnetic spectrum. So on the side somewhere, last little equation, then we'll do 2 practice problems and we are done. Energy with wavelength. If I take this, you don't need to rewrite this. Frequency equals speed of light over lambda. If I throw that in there instead of frequency, so just get rid of that and cover that up, my equation becomes this. Shoot, I wanted it to be a spiky border. Shoot. There we go. That's exciting. All right. So, final 2 problems. Just to show you how you use this. Again, you start doing this, you're like, hey, I'm using energy, I have frequency, this is the equation I need. What energy is associated with a frequency? Oh, I have E and I have frequency. Oh, that's that equation. So I'm going to use this equation, and I'm just going to plug it in. I'm going to plug and chug. the line. Not anymore. And the value may not mean a lot to you, but the next problem will kind of at least bring us to something that we can conclude with in talking about types of radiation. So that's how I would just use it simply as the equation is given to me. Second one, type of wave. Please underline that again. Based on our previous problem, what am I actually solving for then? Type of wave I'm solving for wavelength. Lambda is bless you, is the variable, but you can just say wavelength. And I have energy. Oh shoot, that doesn't have it. Well, here's two things you could do, guys. You could take energy and you could solve for frequency. Then you could take frequency and then plug that in and solve for wavelength, or just do it all at once. Why not do it all at once? Now, I like to rearrange things. If you don't like that, that's fine. But I'd rather have lambda by itself, so these two need to switch places. So it would look like this. And now I just plug it in. I have the H, I have the C. Those are given to me. Oh, the E is within the problem? Done. I did not answer the question. What is the actual answer to my question? X-ray, look on top. I want you to actually physically see it. It's times 10 to the negative 10th. X-ray, I believe, if I'm not mistaken, is like negative 8 to negative 12. Is that correct? So it falls in that range. So that's why I would conclude with X-ray. Okay? We will do the final part. It's really short tomorrow. To me, actually, it's the easiest of the whole thing. It's about just falling and how much energy there is. All right, so please just sit tight. Let's not start conversations. I want to show you something. So on, if you've never bookmarked the website yet, we'll send an email today. You go to Plasky Chemistry, first link, and on the right side there is a link over here. On Monday, it's October 23rd, 10:23 links with, just like you can have Pi Day on 3/14 or anything like that. There is Mole Day. Avogadro's number is 6.02 times 10 to the 23rd. 6:02 a.m. to 6:02 p.m. We only get 12 hours. Kind of cheated out of this. Set your alarm, 6:02. It's called Mole Day. So all across the world, they celebrate Mole Day. So what we do is we amp it up a little bit and have a little fun. And it's not like we're tricking you into mini lectures and like, oh my gosh, at the end of it, I did 3 worksheets. What just happened? You come in and there's 10 events that you're going to be doing or so. I don't know exactly how many, but a good number, from physical events to guessing things to potentially playing a video game, whatever. And you're trying to get as many points as you can, either for yourself if you're competitive or for the team that you're going to be placed on. So there is one, stay with me please. There's an assignment you need to do for actual points. The better you do on it, the more points your team could get. But if you're a bare minimum person, you got to get these in if you don't want to lose points. So you click that link, and you'll see 2 links. Create a mole and color a mole. Okay? If you're like, I'm not artistic, fine. Take your pencil, shade some stuff in and put your name on it and hand it in. Okay? But some of you are going to have actually a lot of fun with this. So let me show you color mole. First, understand the website. These are thumbnails. If I click a thumbnail, it will only print that big. So this is pretty funny though. Mole Wars, may the moles be with you, episode 6.02 times 10 to the 23rd. They're all moles. But, guys, you cannot print it that size. You need to scroll up, and it will always show at the beginning right here. You have to scroll up, and if you click Mole Wars, it's a full page. Okay? My favorite one is guacamole. Ingredients for 1 bowl of guacamole, 6.02 times 10 to the 23rd avogadros instead of avocados. So then you're going to color it. You have to enter it in one of these categories. Most Wisconsin, toughest, cutest, best coloring. Well, how do I do that? You can add things. Let me give you an example. One of the most creative ones I've ever seen. For most Wisconsin, they use this one, Molar Bear. And what they did is they put a Viking helmet on this guy and put him in a Viking jersey. And then these guys were all Packer fans, and they had paintbrushes and paint buckets of green and yellow, and they were running away. And then they had Packer logos all over their igloo. So that was like a most Wisconsin. I've seen, where's the? Oh, there's a cute. They did cutest, and they actually made this a bow tie and like sparkles all over the place, and it was a Mollosaurus Rex, and they made it all cute. So you just have to do one. In the past, everyone's had to do at least two. But you have to, if you're like, I don't know what category, fine, then just put in best overall, and you're like, well, I'm not going to win that. Fine, just that you're not trying to do one or the other. Or maybe you just made really cute looking colors, and you're like, that's cutest. But that's that one. The other one, this is a suggestion, and I have some examples, and you're going to like them. Create a mole. You need to create one now. This is a template. You don't have to use this. If you do, please. This is the inside, though. You cut them out, you color it first, then you put it in there. On the bottom, there's some examples like Napoleon Dynamole, or Molbama, or Moldy Cyrus, or things like that. Here's some ones that I had the last couple of years. And Mr. Blackford and Mr. Kelleher will figure out what they're doing in their room. I have space on top. I put the top 10 winners that stay up for the whole year. So there's like a Milky Way and a Cramola, and there's like, if you've ever looked at them before, there's like 6 crayon moles coming out. This was Nikki Molage. She has a little jacket on here. Here's one with the paper. Did it Clay Matthews? Instead of Clay Matthews? Clay Matthews? Right. Molopoly. And there's actually a Molopoly board. They did Molopoly. Wait, well, I don't want to do paper. Well, okay. This person, this is a molding pin. This one did fabric. This is Molkel Jackson. If you're ever in my room and playing with some of those mold things on the right side by my desk, I actually have there's an aerial sitting on a rock. It's clay. It's the best one I've ever gotten. It was Ariel, the little mole maid. It was perfect. Here's Ronald Moldonald, just paper. Michelangelo. And then, this is one of my top 5 favorite. It's really dinged up now, but I'm going to see if you can figure out what it is. Smoles. So there's chocolate, and then there's a graham cracker on the top. There's Smoles. That was the winner that year, by far. That was really good. It's really beat up now. But, moldy cheese. Moldy cheese. Now, I'm going to bring that up right now. One year, somebody did macaroni and cheese, and it was actually macaroni, like nothing perishable, please. It got nasty in like a week. It was gross. So, anywho, you have to have that by Monday, and all it is one coloring and one guy. Believe me, you start getting into it. People trying to get competitive with it or have some fun with it. If you don't want to be have a lot of fun with it, color whatever you want. Suggestion, just to finish up, and I'm done. Usually stuff the paper ones with like Puffs Plus or something at the end, and then you can tape it or staple them together so they have a little body to them. Mr. Blackford's handing out a sheet. Please understand 2 things with it. It's not until next week. The back sheet we are learning tomorrow. It looks like there's a ton because there's a staple. The back sheet will take the least amount of time, probably 5 minutes to work. The other thing, there's this right here. There's a word bank on the bottom. Usually you put word banks on the top. I'm an idiot. So use the words and place them in there. So it doesn't need to be that hard. Just use the word bank. So you can start working on that.
So how many of those do we need to do?
One of each thing.
So
one coloring and one create. Okay? So we do on mold day, yes. Monday.
How are you?